here we are for 6.2, part 2. We're going to lead off with the calculator, definite integrals on the calculator. This is going to be math key option 9. Okay, if you remember from derivatives, that was number 8, and integrals are number 9. So that's just right here under this math, right here, this math. So math hit 9. Okay, math 9. Math 9. Okay, so you get something that looks like this. On the 84s, let's clear this. You're going to get math 9. You're going to get something that looks more like your notes in the book. You're going to get the integrand symbol, the lower bound, upper bound, place for the function, and then your dx there. So this is a little bit more, it looks visually, it makes more sense. Okay, so you're just going to put in, after you do math 9, you're going to put in the function, x, always, that's standard, always put in x because you're integrating with respect to x. And that's it. So we did this one on the previous page, if you remember, we got 8 pi when we went through and calculated that semicircle. We did a semicircle of radius 4, so we got, the area under the curve. That way we could compute a definite integral by doing the area under the curve. And then another way you can do it, of course, is with your calculator. We don't really know how to do this with calculus yet. So this is the same problem as this one where we got 8 pi. All right? Okay, so into the calculator we go. Let's go with this one first. All right, so square root of 16 minus x squared. So close the absolute value, x, negative 4, and 4. So there you go. There's the function under the root. Close the radicand there. X, negative 4 to 4 in parentheses. And integrals take a little bit of time to think. So just be patient. You can tell the calculator's thinking right here. And don't be alarmed, they take a little time. So while that's going, we'll just do the same thing over here. Lower bound, lower bound, upper bound, in goes the square root of 16 minus x squared. You don't even need to close that parentheses, just pop over to dx. And so that looks exactly like how we do it. And we'll hit enter, and we should get the same thing. Okay, and so over here you can see, and we do, so that's great. So we'll slide this out of the way, and you can see that that is certainly equal to 8 pi. All right, so we're going to use 3 decimal places, so 25.133. So we have a lot of blank space, so I'm going to use this to emphasize 3 decimal places. Okay, you will not get your answers right on the AP exam if you're not at 3 decimal places. And do not over-round within the problem. Round at the very end. Keep your answers within a problem as plump as you can, or either store them so they're completely intact. You don't want to miss a point on the AP exam because you missed this pesky little thousandths. Okay, so we did the sine also. Math 9. We did sine of x. Let's close the angle. Written in terms of x from 0 to pi in a previous example, and we got 2. And so here you certainly get 2 as well. So there you go. Calculator knows its stuff there. And the last one is just the area under the curve. So math 9 of second e to the x cubed. Close the exponent, comma, written in terms of x, comma, from 0, comma, 3. All right, thinking. Like I said, takes a little bit of time. All right, something went awry here. Let's see what's going on, because that is not the correct answer. And that's because I put x cubed. Okay, so let's redo that. Second entry, back this up and do squared. Okay, there we go. 1444.545. 1,444.545. All right, there we go. Yeah, this first one, that was a keystroke error. All right, next part of our notes. This is the limit definition of a definite integral. We are going to actually calculate the exact area under this curve from 0 to 1 using the old-fashioned method. And this takes quite a bit of work. Probably something you're going to want to look over a couple of times before you try to do this. And you will have to do this on a quiz or a test or at some point. Okay, so we're going to do this definite integral from 0, 1. Okay, eventually we will just integrate this. We're going to close that integral. We will just integrate this, use the upper and lower, and calculate this precisely. This other method will calculate this precisely as well. And we're going to go through that right here. So this is the point 1, 0. Okay, here's this coming up. Lock it down to the 1. Maybe my point's a little too low. 1, 0. All right. And this process basically partitions this into infinite rectangles, infinite vertical strips, and pushes those to infinity. So let's go ahead and fill in infinity here. Okay, this is a lot of steps here because it's really showing the whole thing. Our counter is going to be k, so kth rectangle, 1 to n. This is standard, so let's just fill this in so we don't forget it. Okay, so we'll stop there. All right, so drawing the kth rectangle. So here's just some rectangles. Just draw some rectangle like this. Just some rectangle. So if I go here, just some arbitrary point. So this is some arbitrary point within not the left, not the right, not the other point. You would kind of tee it out right here. Okay, so there's this kth rectangle. Just some arbitrary point in the middle. All right. So if we were doing the width of this width is going to be delta x. These are going to be regular subintervals. So it's not going to be delta x of the kth rectangle. It's going to be straight up delta x. All right. So delta x here is going to be b minus a over n, or 1 minus 0 over n. So the width of this is 1 over n. All right. And so if we started, our x sub 0, this starts right here, right? We're going from 0 to 1. So this is your x sub 0. Okay, and then this last piece here is your x sub n. All right, so x sub 0 is here. All right, so x sub 1, I mean, it's going to be so close that you can't even show it, but your x1 is going to be next. All right, so this is 0. And just FYI, we really like these problems when they start with 0. That's a sigh of relief because they're easier if they start with 0. All right, so x to the first, or x subscript 1 can be indicated by 0 plus a delta x. Okay, that's how we jump there, by this 1 over n. All right, so x n can be 0 plus delta x plus delta x. So that is 0 plus 2 px. All right, so to get to this kth, rectangle here, if we get over here to x to the k, how do we get there? This is going to be 0 plus k delta x, all right, or 0 plus k times 1 over n, or k over n. So that's the x value. That's the x value for where we are. Okay, that's the x value for where we are right here. All right? All right. So this is your first step. Again, it's really nice when you start at 0 because this is 0 kind of goes out. You just have this. Sometimes you're going to have 1 plus you know, whatever this is, and those get a little bit more messy. Okay, so let's recall. We're going to do the height, which is going to be f, some arbitrary x within the kth rectangle, so x sub k arbitrary over delta x. Okay, so let's start making our substitutions. So the function here, f of x, is x cubed. So we're going to be plugging in x, k, you know, this here. And now that we've kind of got it, here, it's not really arbitrary. We've got it locked down to this right here. So I can take the arbitrary away. I know what xk is, it's k over n. I know this, so we can take that notation away. And we're going to cube it. All right? And so, you know, what else do we know here? We know that xk is k over n. Okay? And we know that this is k over n. All right. So this is k cubed. All right, this is k cubed. K cubed over n cubed. And this is 1 over, oh, I wrote k. This is 1 over n. Sorry. Delta x is 1 over n. Carried away with my k over n. All right, 1 over n. Okay, so there we go. All right, so let's go ahead and, all right, I'll just keep more steps going. So let's go ahead and do this. So this is k cubed, right, over n to the 4th. Okay, so we are going to use then, we're going to take our sum, okay? So I obviously can't sum up infinite rectangles. It's not doable. But I can use my formulas. So we're going to use our formula right here. Okay, and once you use the formula, that's the sum, so the sigma sign goes away. All right, so this formula here is going to be n squared, n plus 1 squared. All right, this is just n to the 4th. And then this formula is n squared, n plus 1 squared. This formula, this series formula from our series sheet, which is why we did that. And then it's over 4, right? So the series formula, it was that I cubed, you know, the sum of it, I won't write it. You can refer back. I don't want to get into this space over here. But the sum of 1 to n of I cubed was n squared, n plus 1 squared over 4. And this n over 4 is just part of, you know, the function is cubed, and then that delta x is at that additional n. All right, and so we're going to take the limit of this. Okay, so once you get going, when we push the limit in here, we're going to be looking for the leading term. So, you know, this is going to be, you know, resembles. I'm going to carry it through, but, you know, this is going to resembles, be a resembles function, or even, better word, the power function here. You can see it's going to be n squared and n squared, just into the 4, over 4n to the 4. Okay, and when I push a limit of infinity, those are your shortcuts. Those are your horizontal asymptote shortcuts whenever you see this push to infinity. And so, you know, what's happening on the far right, that's a horizontal asymptote. And the exponents match. So you do coefficient over coefficient. So this answer is going to be 1 over 4, the exact area under the curve. And we'll do that on the calculator too, so you can see that. All right, so let's just take this out of the picture and just look at it all the way through. The limit as n approaches infinity. So this is going to be n squared, n squared. It's going to be n squared plus 2n plus 1 over 4n to the 4. Limit as n approaches infinity of n to the 4th plus 2n cubed plus n squared over 4n to the 4th. And again, with your shortcuts, you get 1 over 4. Okay, so in terms of area, that would be units square, but whatever you're accumulating, you want to multiply the two axes together to actually get the correct unit there to see whatever you're accumulating under. What does this area represent in context of, say, a word problem? Okay, let's look at the calculator here. Check it out. So, math 9, okay, we're doing x cubed, comma x, comma 0, comma 1. There you go, 1/4. Woohoo! So, this is an interesting problem. We'll go through some more where we start not at 0 and take a look at what that looks like. Okay, so you want to look at this, use this sort of process when you're asked to do the based on the definition of a definite integral. So, like the limit definition, or Riemann sum definition, limit def, they might say limit definition of an integral, the Riemann sum definition of an integral, something like that. Okay, so this process is similar to the concept of doing the definition of a derivative based on the limit as h approaches 0 of the difference quotient. Okay, remember this is that's a derivative, and as is this is a definite integral. All right, good.